Let's look at figure 4.11, an illustration of pH. In this figure we have a strip that runs from a value of 0 to 7 to 14, and this strip is colored from red to sort of a grayish color to blue. These are the colors of litmus paper, something you may have seen in the laboratory, where you found that blue paper turned red in the presence of acid, and red paper turned blue in the presence of a base. Well, this is exactly what we're trying to illustrate. And on this strip, we've imposed some household products as well as blood, and we show that vinegar and soda and an orange all have pHs in the range of 2.8, 2.9, 3.8, relatively small values. Here, just above a pH of 7, we have blood at a pH of 7.4. We have ammonia and household cleaner with pHs of about 11 and 11.7. You know that ammonia is certainly a base. If you've ever used it to clean things, you know that it has a slippery feel, one of the characteristics you may have learned of a base. And oven cleaners usually have sodium hydroxide, which you know is a relatively strong base. Now that you've seen the pH scale, how is it defined mathematically? The standard equation defining pH is that it is equal to the negative of the base 10 logarithm of the hydronium ion concentration. If you know the hydronium ion concentration, you can quickly calculate the pH. An alternative equation, that's really the anti-log of the basic definition, is that the hydronium ion concentration is equal to 10 to the minus pH power. This is a particularly useful equation in the laboratory because we often measure the pH using a pH meter, and then we can calculate the hydronium ion concentration from that. Both of these equations are very useful, and you'll see them throughout your chemistry class. Now that we have a mathematical definition of pH, let's connect that better to our pH scale. One of the things that we find is that for a neutral solution, one that is neither acidic nor basic, the hydronium ion concentration at 25 degrees Celsius is 1 times 10 to the minus 7 moles per liter. And that means the pH of a neutral solution at that temperature is 7. If the hydronium ion concentration is greater than 10 to the minus 7 moles per liter, that means the pH ranges somewhere from 0 up to 7, and the solution is acidic. Let's say the hydronium ion concentration is 10 to the minus 3. The logarithm of 10 to the minus 3 is minus 3, and so the pH is plus 3. Alternatively, if the hydronium ion concentration is less than 10 to the minus 7, the pH then ranges from 7 up to 14, and the solution is basic. Let's say the hydronium ion concentration is 10 to the minus 10. The log of 10 to the minus 10 is minus 10, and so the pH is plus 10, a basic solution. All right, let's do a few examples of these calculations, and then we'll give you some more to try on your own. Suppose you have a solution whose hydronium ion concentration is 2.7 times 10 to the minus 3 moles per liter. What's the pH of that solution? Well, the way to solve this is to use the standard equation for the calculation of pH from hydronium ion concentration, minus the log of the hydronium ion concentration. So we'll put our concentration in, and then find the logarithm of 2.7 times 10 to the minus 3. And you'll find that that is minus 2.57. Well, there's already a negative sign in front of the equation, so that means that the pH is plus 2.57. This is a relatively low pH value, and therefore the solution is pretty clearly acidic. All right, let's try another problem. What's the hydronium ion concentration when the pH is 8.36? Here we use the other equation that relates hydronium ion and pH. That is that the concentration is equal to 10 to the minus pH power. So we'll put minus 8.36 into our expression. And one of the things we want to warn you about is to be sure to put that minus sign in. That's a relatively common student error. Well, now you can use the 10 to the x function on your calculator or a similar function, and you'll find that the pH of 8.36 gives you a hydronium ion concentration of 4.4 times 10 to the minus 9 moles per liter. This is a relatively small value of the hydronium ion concentration, a large value of pH, and so the solution is, again, pretty clearly basic in this case. Now that you've seen these couple of examples, let's try some more on your own.